Middle school.
Middle school, of course I did. I haven't failed any exams except for Spanish.
All right, guys, let's go.
No, I had a C. It's Spanish 4 though, so it's fine.
We're doing rotational or angular motion with an emphasis on, you said momentum, right?
Yeah.
All right. So just a brief reminder before we start any of this, the only real differences, the only thing that we have to really be focused on is the idea that angular motion and linear motion are largely the same. When we talk about angular motion, though, one of the important details is that your object, no matter how it's shaped, has a single point within it that will act as the pivot point for the system, and the object rotates about that pivot point. Now, the distribution of the mass about the pivot point determines its inertia. That's one of the most important distinctions when we deal with rotational motion versus linear motion, is that an object's momentum is based on, again, is its inertia while moving. But when we deal with inertia, we don't necessarily deal with the mass of the object for rotation. We deal with how its mass is distributed. So a piece of the object here has a different velocity and is therefore harder to get to move than a piece of the object right here. That's what it came down to. When we talked about it, we started with the idea of kinetic energy. And we said a rotating object might not change location, but pieces of the object are. They're moving. So a piece farther away from the axis of rotation requires more energy to get up to speed than a piece of the object that is closer to the point of rotation. Because of that, we indicated that the inertia of the system is going to depend on where each of the pieces of the object are compared to the axis of rotation. Sorry guys, we just started. Were you able to get your wallet okay?
Mm-hmm.
So if we just consider these two pieces individually, piece 1 and piece 2, piece 1 is a distance r1 away and piece 2 is a distance r2 away. Piece 1 is going to have more inertia. It's going to be more difficult to move than piece 2 is because it's so much further away from the pivot point. So our shape of our object determines how much inertia it has when it's going to spin. That's the biggest takeaway. And we should, in a general sense, in a big overview, it should be kind of clear that rotational kinetic energy and angular momentum all depend on how far away the mass is from the pivot point. Again, the shape of the object. You see, the one thing that can actually change angular motion problems and make them much different than linear motion problems is an object's inertia can change merely by changing the shape of the object. Now, to be clear, any object's inertia can change if its mass changes. So rockets, they're always getting rid of mass. Their inertia is changing. They're generally having less and less inertia the longer the rocket engine fires. Your car, technically, is having less and less inertia the more it burns fuel. Because after a while, you'll have an empty tank. It weighs a lot less than the full tank. So when you go to fill up your car has less inertia before it's been filled up than after. But we tend to not do problems like that. They don't tend to show up. You know, knowing that you're burning fuel and changing your inertia does affect the system. So technically, your car should be able to accelerate faster just before it goes on empty than when your car has been fueled up, because the engine is acting on less mass. But we tend to see that exaggerated in rotational problems, where an object's mass doesn't have to change. All it has to do is change its shape. So that brings things like the ice skater who pulls their arms in. They're changing their moment of inertia, but they're not changing their mass. But because they can change their shape, they change how difficult they are to keep moving. This is going to affect any problem that has conservation at the root of its or at the core of the principle of the problem. So when we talk about conservation of momentum problems, where the object's shape can change, then we're going to have issues to deal with when it comes to its momentum, because the momentum of the system will have to be conserved, but the inertia of the system doesn't have to stay the same. So let's look at those problems first. And there's I described 3 or 4 different styles of this problem. Let's look at the simplest, and that's kind of the merry-go-round problem. Just to be clear, the merry-go-round problem actually offers us about 3 or 4 different good examples for the way in which angular momentum can be asked on the exam. So let's start with the simplest. Let's start with trying to get something like a merry-go-round to get spun up. So let's assume that our merry-go-round is just a disc. The disc itself isn't changing very much. So that represents the center of the disc. Now, let's describe a couple methods that we could use to get this system to actually start to spin. Let's assume that it's not spinning right now. What's the simplest way to get it to spin? Apply a torque, sure. Have somebody walk up to the side of it, apply a force this way, and that will get the object to spin. Now, since this is an overview, consider all of the plausible things that force can do. First, it should be clear that that force is being applied at the edge of the object, therefore it constitutes a torque. So that force is a torque on the system, with the angle going to be 90 degrees. Unless I tell you different, assume. Now, is the object's angular speed going to change? If you think it's going to speed up, it's important to realize that that torque must be doing work, because it's going to change the kinetic energy. I'm trying to focus right now on vocabulary a little bit. They're going to say things on the test, and you have to see they're asking me how much work was done spinning him up. What are they talking about? It's just some kid pushing a merry-go-round. That's the connection. If you're pushing on a merry-go-round, you're applying a force to change its speed. That's going to be work. That's the definition of work. Anytime you change something's speed, you change its kinetic energy, you're doing work on the system. What's that? Work work actually is other things too. Changing an object's location requires work in most cases, but anytime its velocity changes, is automatically work. Automatically. Yeah. Now, the angle at which you apply the force when it comes to doing a torque is actually a critical value, just like all of them are. They are all of equal weight. So I've drawn it so that it's tangent. This is the most efficient way to apply a torque, because the entire force is perpendicular to the torque arm, and that's the most efficient way to apply a torque. At the same time, if you have some idiot kid over here who's pushing this way on the wheel, he's wasting some of his force, because the thing is, it's stuck in the ground, so he's not going to be able to get the entire merry-go-round to move this direction. But that makes his force less effective, because the only part of the force that actually can contribute to the spin is the part that's this direction. So the angle is actually a critical value. And applying it at different angles will do less work, because some of that force is doing no work at all. Right. You, numerically, you'd have to figure it out. Now, in this part, because the sine is a scaling value between 0 and 100%, you guys don't think of sine as being like a percentage, but it really is. Because sine can only be between 0 and 1. So it's truly a real percentage. If you want to find out what angle produces 50% of the torque, then you have to find out when the sine is 50%, 30 degrees. So it truly is a real percentage that scales how much torque you get from your force. Now, there's no way to eyeball it. If they're giving you numbers, you're going to have to work it out and figure it out. But there's no easy way to eyeball it. Now, that being said, there are some things you can't do. Meaning, the angle can never be greater than 1. So if there's an impossibility of there being a scale that would produce greater than 1, you know that you have to go with the one that gets you the bigger value. But at the same time, you're probably just going to have to work it out. Now, the last thing I want to tell you is that this force, because it causes a change in velocity, also imparts an impulse. I didn't talk about impulse as much this year because the word just doesn't come up that often. But impulse is any change in momentum, including changes in angular momentum. So torques can do work by changing velocity, and they can apply an impulse by changing momentum. This is not the only way to get the merry-go-round to speed up, though. It's one way. So let's talk about some other ways to get the merry-go-round to speed up. First, this speaks to the rocket problem, because that was what was asked specifically. The one thing about a rocket problem that you should probably infer, though, is that if you want your thing to stay in place, your space station to stay in place, merry-go-rounds stay in place because they're mounted to the ground, and therefore the ground can apply a force to keep the whole thing from moving to a different place. So that's happening right now. The spindle is applying a force this way. It's acting at the center of mass, so it doesn't apply a torque, but it keeps the entire merry-go-round from sliding off the playground. Now in space, you don't have that. So if we're talking about a space station that they're going to spin up, you have to realize that you need to have a counterbalancing force so that the net force is 0, but the net torque is not. And it doesn't have to be 2. It could be 3, as long as those forces are applied so that the net force is 0. Does everybody understand what I mean by that? So that the force is 0, but the net torque is not. But let's get to the other thing that can happen. This is one way to get this thing started. I'm worried about this next one, because I think it's one that we'll forget, and it's not terribly hard, but I believe students will be full-blown confused if it's on the test.
Do you know what to ask, like, if a kid is going to the center or if the kid's walking to the outside?
I'm gonna go through that real quick, because that's the third thing I want to talk about too. So let's say this is how, if you're by yourself and you're at the merry-go-round because you have no friends, thus my life. No.
Oh my God.
I had friends when I was a kid. But if you're by yourself, if you're the loner and you wanted to ride the merry-go-round, you could, of course, step onto the merry-go-round and just drag your foot to get yourself started. But there's also the more fun way, and I don't know if you guys did it.
No, jumping on.
But running and jumping on.
This was the extra credit for that test, right?
Yep. Now, depends on which test you had. If you run and jump on, this is a problem where the person that's running towards the merry-go-round, when they go to jump on, the act of them jumping on applies a torque to the merry-go-round and gets it to move. That's effectively what it is. But it's so much more complicated to think of it that way than to think of it as a conservation of momentum problem. And before I do that, this is the same problem. This person has momentum, but they're going to transfer that momentum to the merry-go-round. The difference is that we tend to think of this person's motion as being linear momentum. And this is the most important thing you probably write down. Linear momentum and angular momentum are different quantities. They're not the same. unlike linear energy and angular energy, which are the same measurement, momentum isn't. And the most important detail you need to write down is that angular momentum has a point of reference. The pivot point. It is the point of reference. Again, the pivot point is our point of reference. So even though the kid isn't part of the merry-go-round yet, the merry-go-round's pivot point becomes our point of reference for the kid. He has angular momentum about the pivot point, even though he's running in a straight line. Now, you guys who have those mathematical heads of yours, think for a moment. As this guy runs, after a few moments, he'll be right here. Does that make sense? Let's say that their velocity doesn't change, so mv is the same, but what's happened to r? It's definitely gotten smaller. But angular momentum for a point particle is r times mv times the sine of the angle, just like it is for torque, where this is the angle.
Wait, what is that, L?
L is angular momentum for a point particle. We don't use capital L because physics does stupid crap like that. Now, as the kid's running, the R is getting smaller, but the angle is getting bigger. Do you guys notice that? It can be shown that they change in the same proportion, which is why this is a constant for a person moving with a constant velocity. Now, guys, if you remember only one thing about this, what I'm about to say is the most important piece. Because it doesn't change, that instant when he jumps on, when he is right at the edge and he jumps on, when he is at the radius, at that moment, if he does it right, the angle should be 90 degrees. Which means if he jumps on at the edge of the merry-go-round, his angular momentum will be RMV. If he jumps on at the edge. The reason I want to bring this up is because this is called the R perpendicular. And it represents the same angular momentum as if he was way out here. So often we tend to consider this object's angular momentum, but consider it from the point where he jumps on. So if a kid's going to run and jump onto the merry-go-round, and they tell you he's going to jump on at its edge, this is the angular momentum of the person. The radius of the merry-go-round plus their momentum. Their angular momentum is still just their momentum and the radius. It's like the torque. Right? When you apply a torque on a pulley, it's the force and the radius. When you have an angular momentum collision like this, it's going to be the momentum and the radius. They jump on, that's their angular momentum. Now, I've kind of made a mess of this picture. So, a mess of a new picture, and look at what this problem would actually look like to make it kind of like the one we had for our sample. So here's the before case. It's the kid running towards the edge. And then there's the after case with the kid on the edge and the system's rotating. So before and after. Just like before, for the other kind of collision, the momentum is going to be conserved. So when we talk about conservation of momentum, we're going to have the momentum of the person who's running, which I'll use a lowercase l because it's angular momentum for a point particle. And then we'll have the angular momentum of the merry-go-round and the kid afterwards. And these have to be equal. Now, when we look at these problems, you do have a choice. You have a choice to consider whether you want to combine the kid and the merry-go-round to one object with one moment of inertia, or whether you want them to be separate objects with the same velocity. It's your choice. And I think it's easier just to combine their moments of inertia and make it one object with one moment of inertia. But you can do either. It doesn't make any difference. The important thing is, when you see a problem like this, if they do not give you how far away he is when he starts running, then just note that his angular momentum will be RMV. However fast he's running in his mass times the radius of the ride. Now, when he's on the ride, the way I like to think of these problems is that there's the moment of inertia of the ride plus his moment of inertia, which is the moment of inertia of a point mass, mr squared. It's always mr squared for a point mass. And that's going to equal the angular speed of the system. You're still just going to set these two things equal to each other. And there are some obvious things that increase the speed. If the kid runs faster, it increases the speed. If the kid has more mass, it increases the speed. The radius doesn't automatically increase the speed, because you'll notice there's going to be parts with radius on the top and parts with radius on the bottom there, right? Because I have it also listed over here. So you can't guarantee that it's going to increase the speed, and so I wouldn't. But remember, if you do increase the radius, you do increase the amount of torque he applies when he jumps on the ride. So when we're looking at how he affects the ride because he's running, the most effective thing he could do is just run faster. Now, before we go any further, we actually look at something I think you guys will want to know too, is what if he runs towards the center of the ride? Will he be able to make the ride rotate by running towards the center? No, he can't apply a torque. More importantly, and this is the part that could come up on multiple choice, he has no angular momentum if he runs towards the center. He only has angular momentum if there is an angle between him and the pivot point. If the angle's 0, there is no angular momentum. That's why he can't cause the ride to turn. He's the town idiot who keeps running at the ride but doesn't ever spin. If you've ever been to a playground, there's plenty of those. All right, so let's do one more. And this is the one I think two of you asked about and I think is worth looking at. I have a merry-go-round that's already spinning. There's a kid on it, and it's already spinning. The kid decides to walk to the center. Now, this is one of those problems where it's easy to become confused about what changes. Can the kid walking to the center affect the speed of the merry-go-round?
Yes.
Sure, we've had that conversation a lot. Can the kid walking to the center change the momentum of the system? No, he can't. He can't change the momentum of the system. He can change his angular momentum, and he can change the merry-go-round's angular momentum, but he can't change the system's angular momentum. Think about it for just a minute. If he walks to the center, will the system speed up or slow down?
Speed up.
Speed up. So the merry-go-round is going to have an increase in angular momentum. Is he going to be going faster or slower when he's towards the center? He's going to be going slower, so he has a decrease in angular momentum. while the ride had an increase. Meaning, if he's a part of the system, he can't change the momentum of the system. So again, if he walks to the center, he can change the speed, sure. He cannot change the momentum of the system. He can change his angular momentum, and he can change the merry-go-round's angular momentum, but the system's angular momentum is the same. Go ahead.
So how is his momentum changing?
His velocity here is going to be bigger than the velocity here, because when he's in the center, he's making a smaller circle. The whole thing has one angular speed, so his velocity will be smaller. So his total angular momentum is smaller. Now, I think all of you recognize that him walking to the center will increase the speed of the system. And if you want, just a real brief look at it. Right now, the moment of inertia of the system is 1/2 mass of the merry-go-round times the radius squared plus his mass times the radius squared. This is the moment of inertia of the system. If he walks to the center, his R becomes 0. So the new moment of inertia will just be 1/2 mr squared. His contribution disappears. That means the angular momentum that we started with has to increase to compensate for the loss of inertia. So he's going faster. Now here's the part that you guys tend to have problems with, and let's nail this from the beginning. Just because the angular momentum of the system didn't change doesn't mean he didn't do work. Did the velocity of the system change? The velocity of the system changed, work was done on the system, period. Yeah, the moment of inertia changed a little bit, but work was done on the system. There was no impulse because there was no change in momentum, but there was work. Again, there was no impulse because there was no change in momentum, but there was work done, and it's because kinetic energy is the square of the velocity. So even though the moment of inertia decreased, because the angular speed increased and it's squared, there's a change in kinetic energy. He does work. And it's real simple. It's hard to walk to the center. You guys who spun on the chair and had to pull your arms in, it's hard to pull your arms in. You have to work against a force to do so. You're doing work because of it. And that's why there's an increase in energy when this happens. And the energy is coming from him. He is losing energy and giving it to the system. He's doing work on the system. Does that answer all of your questions?
Mm-hmm.
Is that pretty clear?
Yeah.
Do you want to talk about the spaceship version of this one?
Isn't it like the same thing?
It's exactly the same.
Then no.
All right. Yeah.
So mostly going to be just concepts rather than like math?
You guys have seen all the FRQs I have to give you. I would say that it's, how many of you would agree? It's probably 2/3 conceptual, 1/3 mathematical,
Yeah, like the
with
first
part of the
part's
math being laboratory kind of analysis. So I tend to write some of this stuff out, but I also am trying to state, pretty unequivocally that if this value is changing, what values are changing in response. And I think that there are a couple of banner ideas you should be able to say. First, the system accelerated. There was a torque applied to the system. It's from his feet on the merry-go-round. He definitely applied a torque. That torque did work because it sped up the system and changed the kinetic energy. That's the use of vocabulary, right? You could say that he walked to the center, the energy increased. You could say that, but specifically his feet apply a torque. That torque increased the speed, and because there's an increase in speed, there's an increase in kinetic energy. All of those pieces are also true, and I think those pieces are important. All right, that was angular speed and angular motion. Any questions? Yes.
That at the top right, that's for
Yes. Yeah, and it's probably not real clear, but it's moment of inertia times angular speed squared. Julie?
This is different, but like, we know that like he knows about the instantaneous velocity.
Sure. Let me start. Think of this problem. If you have a skateboard and a person running at it, if they run and jump on the skateboard, after they collide with the skateboard, the whole system will be moving to the right. We've seen problems like this before. It's mv for the guy that's running, plus, well, there's zero momentum for the skateboard if it's staying still, but then after he jumps on it, it's mass of the person plus mass of the skateboard times their combined velocity. Right? We did this in the lab. We had the cart crash into the other cart and they both moved to the side. That problem is a clear conservation of momentum question. It's not particularly interesting. It's going to be on the exam. This is the one you're probably going to get right. The important detail is that the person actually applies a force to the skateboard. They do. And the skateboard applies a force to them. Their force speeds up the skateboard while the skateboard's force slows down the person. But we would never do the force part of that problem. It's too hard. We don't know anything about how long it took or any accelerations. We just know that afterwards the system's moving slower than before because all of a sudden the inertia increased.